Hello, everybody. Welcome to the third webinar on Elmer FEM webinar series. And this one will be still given by CSC team. And I'm the product manager of Elmer here at CSC. And I will be doing most of the discussion today. And here I have my colleagues. Please.
Yes, hello, this is Mika Kanerva, also from CSC. I'm here part of the organizing team, taking care of some of the practicalities with the webinars. And joining us, we have our other presenter today. Thomas, please.
Yeah, hello, my name is Thomas Zwinger, and I'm here to give you a little bit of online coding demo or online presentation of how to run Elmer in parallel.
Okay. So we have some practical guidelines that Mikael will go through with you. So please, Mikael.
Yes, especially for those of you who are joining us for the first time, this is addressed especially to you, and for the others, this is just a repetition of what we've told you the previous times we had this webinar. So we have this Q&A function in Zoom, and you will find the Q&A button at the bottom of your screen. So please write all your questions relating to the presentations and the ones addressed to the presenters in the Q&A window. There's also a chat. Chat we use mainly for delivering general information regarding the webinar, but it can also be used for general discussion if you so will. The presentation slides are going to be available at the URL address you see on the slide. I'll put the same address in the chat window soon. And this, as you see, the webinar itself will be recorded and will be available on Elmer FEM's YouTube channel. I'll also post the address to that channel in the chat window in just a moment.
Thank you. So here is the program for the webinar series, and as you see, the three first ones are given by the CSC team, and next week will be exciting because we will have some external contributions. So Juris Vencels will start the external contribution series, and we'll talk about the Elmer OpenFOAM library. Maybe I won't go through the rest of the program, but I think that this will certainly be very interesting talks. So today we will talk about parallel computing with Elmer. So as you know, we come from the CSC IT Center for Science in Finland, and actually CSC started off as a sort of supercomputing center. Now we are many other things too, but sort of because of our roots, the parallel computing has a special place in our hearts. And here is some outline for today. So I start with some words about algorithmic scalability, then go on to present the linear solvers and preconditioners available in Elmer, and talk about some parallel computing principles, strong and weak scaling. We will show how to partition meshes, consider the differences between parallel and serial solution, and show some examples that have been pre-computed, and make or have a few words about architecture developments and how they are influencing Elmer development. And in between, Thomas will have a nice demonstration addressing many of these same things. So before going to really parallel computing, I want to sort of emphasize the algorithmic scalability. So whatever algorithm you use, it has a sort of characteristic scaling. Of course, it partially depends on the implementation, but whatever your implementation is, you cannot systematically beat this sort of scaling law. So you know that your different algorithms will have different scaling laws, and this is sort of the starting point that you should always bear in mind, that choose the algorithms, if possible, that scale well if you intend to run large jobs. If you run only small jobs, then often it doesn't matter whether your job is large or small, but here if you run really large jobs, then this is of major importance. So here I have done quite long ago some comparisons between different sort of implementations of algorithms in different codes. So this has included GMesh, Elmer grid, and Elmer simulations, and all these have been almost linearly scaling. But you can see that the structured meshing, which is actually straightforward, it takes very little time. Partitioning takes a little bit more time. The unstructured meshing in GMesh takes a further little bit more time, and the solution takes usually the most of the time. So when you start to sort of resolve the bottlenecks, you typically start from the one that consumes the most of your CPU time, which is of course the solution. But if you have a very large problem, then also meshing may become bottleneck, etc. But so the key line here is that these all almost scale linearly. Here I have compared two different sort of families of preconditioners. So using the same Krylov method, which is basically a solution method for linear systems, using different preconditioners, incomplete LU, which is a one-level preconditioner, and multigrid preconditioner. And you can see that as the problem size grows, eventually these multigrid preconditioners will beat the sort of one-level preconditioner, such as LU. And we can measure this. So here there is a simple formula. So we make some sort of numerical experiments and fit the alpha and beta to this simple equation. So the prefactor, of course, tells here what's the time used for 1 million degrees of freedom, and then the exponent tells how does it scale when the problem size grows or diminishes. And you can see that these methods here, they scale almost linearly. So your exponent is about 1.1, and these are all this CMG is short for clustering multigrid. So these are all multigrid method based preconditioners. And then at the bottom of the stack, we have direct solvers, which typically for 3D problems do not scale that well. So, and in between you have Krylov methods with one level preconditioners, which actually for this case also scale quite well. But this is of course a very simple case, so you are not often seeing this kind of scalability with these one level preconditioners. And so of course, if you run large jobs, you should look at the sort of methods here that scale rather well. When you start using different linear solvers in Elmer, you of course see something like this. So you have a set of keywords where you define what is your linear system solver type. Is it iterative or direct? That's the main choice. Then you have sort of choices between iterative methods and direct methods. And for iterative methods, you have also a set of additional parameters like what is the linear system max iterations? So how many times will you iterate? When do you stop iterating? And what happens if you do not iterate and find convergence? And you have to choose the preconditioner. And also some different methods have their own keywords, etc. So you will find these at the Elmer solver manual, but this is something that you would typically see, and it's often a good idea to sort of alter these strategies and try to find the best strategy for your given problem. The linear solvers that can be used with Elmer can be divided into sort of those that come with Elmer. So we have, since the dawn of Elmer, we have the hood iter library that comes with basic Krylov methods, and recently, let's say during the past few years, we have added some additional methods like GCR, IDRS, and PCK stub L. So together, these sort of form the backbone of the standard Elmer iterative solution. We have some multigrid methods which are not terribly robust. So multigrid method is sort of set of sort of recipes, and this does not include sort of all the best recipes. So it's sort of rather basic implementation. But you have external libraries, iterative libraries, where you have much better recipes. So like if you go in parallel, you have Hypre, which often comes with Elmer. So typical Elmer installations, like the virtual machine, comes with Hypre. This is a library coming from Lawrence Livermore National Laboratories, so I think they know what they are doing. And this often provides the best methods for very large problems. Additionally, there are some other sort of iterative methods that are sort of more experimental or that are a little bit difficult to compile with. So Hypre is rather straightforward, and that's often therefore the choice. We have also direct methods. The banded methods comes with Elmer, but it's not to be recommended unless you are solving 1D problem where the bandwidth of the matrix is very narrow. We use UMFPAC in quite standard manner. It's from University of Florida, very nice direct multifrontal solver. And then we have MUMS, which is the best strategy, maybe best free strategy at least, for parallel direct solution. And then we have some additional interfaces like also for MKL parity, so that comes with many pre-installed libraries in supercomputing centers, for instance. I have mentioned the word preconditioning a few times. So what is the preconditioning? So actually, many times our job is a lot about preconditioning. So the software developers, at times we have spent tens of % of our time finding and implementing sort of tailored and robust preconditioners for various problems. So we are solving a linear problem, and instead of solving the original linear system, we try to solve here the left preconditioned system. So here the P is an approximation of the inverse of A. So if we would be able to accurately estimate P, then of course it would be inverse of A, and P times A would be a unit matrix. But as this is not the case, it's close to maybe unit matrix. So you can think that, okay, then it's rather easy to sort of iterate the X to sort of convergence. So the simplest, for instance, preconditioner is taking just a diagonal of A and using that as a preconditioner. So this is also something that you get if you just do scaling. So there is unfortunately no strict guidelines what preconditioners to use. So it's sort of a little bit like experimental science. So you have different choices, but you don't know before you try out what is the best method for your given problem. P may also be considered not a matrix, but a sort of a operator. So for instance, multigrid as a preconditioner it's more like an operator, not a matrix that you operate this with. The goal of preconditioning is to reduce the condition number. So that means that you have a more robust iteration and a faster convergence of the linear systems. And typically, you have a combination of Krylov method plus then a preconditioner. So, and I would say that the preconditioner is even more important than the Krylov method. Parallelization adds some complexity to the preconditioning because many of the preconditioners, they are not exactly the same in parallel. So, for instance, incomplete LU is typically done, at least in Elmer, it's done partition-wise, so it's not the same in parallel. Its converge is quite okay-ish, so quite the same in parallel and serial, but it's not the same. So it's difficult to compare like then the solutions like one-to-one. For instance, in the iteration count, etc. So we have a number of different preconditioners in Elmer. Also in Hypre, there are a number of different preconditioners. And if these fail you, then I suggest that you look at the ones that are given by Hypre. And of course, the Hypre preconditioners are then also used by the Hypre sort of Hypre linear solvers. Okay, I think in this stage we will ask the question. So I think we have a poll. Maybe somebody can open the poll and ask the question. Okay, so.
Oh, yes, we can launch the poll, and the poll has been launched.
Yes, so the question is, how many cores do you utilize in your simulation? So in order to not to give sort of a very boring answer, don't answer that you usually use one, because that's what we all also do. So, but what's sort of the largest that you use sort of in a somewhat regular basis? So. Okay, I think we have a representative solution. 5, 4, 3, 2, 1. Finished. I think we can end the polling. Okay, so it seems that over half of you, so 60% of you, do use some sort of parallel computing. But you probably do it on your own PC, because current day PCs often include this 2 to 8 cores. Then 1/4 of you are using sort of more than a sort of regular, at least a cheaper PC would have. Maybe also you use some sort of more advanced or more expensive multi-core CPU, which they come today like with 16 or 20 cores even. And it seems that we don't have anybody from a supercomputing center that would have been sort of running with 256 or above jobs. So let's keep that in mind. So typically people seem to be like, even industrial problems, they are not solved with thousands of cores, but we should be able to use tens and even some hundreds of cores. So shortly about some parallel computing concepts. So there are different types of architectures that are existing in computers, and the main sort of choice is between shared memory and distributed memory. So like a typical supercomputer would have shared memory only between the cores within one CPU, so these can access the whole memory within that CPU, whereas then the distributed memory in the system cannot be accessed by any given core. So you have a sort of combination of shared and distributed memory in typical systems. So you have some sort of heterogeneity in your memory architecture. And depending on what kind of sort of memory model you have then accordingly a different choice of programming models. So if you have shared memory, then you would typically use threads or like OpenMP. So you know that you don't have to make some maneuvers to sort of access the sort of data, but you just can sort of take it given that you have access to that data, and these programming models are in a way a little bit simpler. So you just sort of implement efficient ways to loop over the data, etc. On the other hand, you have, for distributed memory, you have the message batching interface where you have explicitly communicate all the data that you want to share with the other partition or the other process. So these models usually are used when you aim higher in your sort of scalability, because they scale up well up to thousands or tens of thousands of cores, or even hundreds of thousands of cores. So massively parallel FEM codes typically use MPI as the main parallelization strategy. Programming with MPI is not simple, but luckily most of the stuff has been sort of hidden by the end user. So you actually, with Elmer, you don't have to know whether your model typically is serial or parallel. They look exactly the same. The linear solvers take care of the communication typically. So the parallelization comes with also two different flavors of scaling. So you have strong scaling. Strong scaling is used as a measure when you have a fixed problem size, and then you increase the number of cores. So here, the optimal case is, of course, that the number of processes or cores times the time is constant. So on the other hand, that means that if you have 4 times as many cores, then your time should drop into 1/4. Typically, if we have enough elements in a partition, we can achieve good, strong scaling. If the number of elements falls too small, then the scaling suffers. Then we have weak scaling, which is more a measure of the algorithmic scalability. So you cannot really beat, systematically at least, the algorithmic scaling law. So here we look at a problem that grows with the size of the number of processes. So if we start with a small serial case, then and we start using 4 cores for it, then also the problem size is 4 times bigger. So these are 2 different measures which measure a little bit different things, but of course, optimally we would like to have both sort of good. So to real parallel workflow here, this I think applies to most finite element solvers, but this is specifically for Elmer. So typically we do meshing in serial, partitioning in serial, and then assembly is done in parallel. So in partitioning process, we divide the mesh into roughly the same size partitions, and for each of them we do independent assembly, and then we do solution. Both of these processes may need to change some information, which is then carried out by these MPI instructions. And then we do finally visualization that is also done typically in serial. So this kind of workflow easily scales up to tens or hundreds of cores. You don't have to so much care about these pre- and post-processing steps. And of course, these pre- and post-processing steps, they come with certain software, and the solution is mainly taking care of Elmer, but it can utilize like external libraries for the solution of the linear system. Here are some examples about partitioning. So partitioning typically is done using Elmer grid. So it's the annoying program that you start to sort of manipulate the mesh prior to starting your simulation. You can also access, I think, this via Elmer GUI, but typically you do it on command line if you are working on especially on a supercomputer. So we have 2 main families for mesh partitioning. The Metis graph partitioning. There are also other libraries for graph partitioning, but Metis is the one that Elmer Grid uses. So basically, it takes the computational graph, so the connectivity network of the finite element mesh, and then uses only that to sort of make some heuristic partitioning, which aims to minimize the communication. So you can see that, wow, this is pretty nice. So I could assume that this sort of communication needed between these sort of partitions to exchange information between them is sort of well sort of minimized. Actually, you cannot sort of easily show the best sort of partitioning, because it's in order to show what is the best partition, you should go through all the combinations of the partitionings, and that's not humanly possible. Or you can also do division by Cartesian directions. So here, for instance, we have done partitioning in y direction, and here in 2 directions recursively. So these are of the same size, but actually you can see that they are really poor in minimizing communication. So you should know your sort of algorithm also here. So use the one that is ideal for the case. So for instance, here I had a structured mesh. So if I use this part cell, which sort of divides it sort of in a uniform sort of cells, then this is absolutely perfect. So you could not have a better partitioning for this case if you want 4 partitions. But like Metis here, it doesn't really probably minimize the communication here. Of course, partitioning into 8 is more complicated than partitioning to 4 here, but still, I don't think these are optimal. I would bet that this one, for instance, is more optimal in minimizing the communication. And on the other hand, if we have a sort of unstructured mesh, which has no regularity in the graph, then certainly these, for instance, this one is not good at all. It's really bad. So I would bet this is the best among these. So know your sort of mesh and only use the geometric one if you sort of have a very regular simple mesh. You may have a special problem where you need to sort of have information from the neighbors. This is the sort of the area where you need the information. You can call it halo elements. So for instance, here, if you have discontinuous color scheme, you need to sort of have a little bit more information on the interface so that you can communicate the fluxes between or set the flux conditions over the interface. And for instance, here, this sort of imitates to be a rotating machine. And here, in order not to sort of create connections between rotating partitions, we sort of can, by construction, have a partitioning and also halos that sort of enable and minimize the communication for these rotating machines. So I think at this stage I give the floor to Thomas. So Thomas has prepared some nice demonstration, so you don't have to listen to my boring slides. Please, Thomas.
Yeah, well, no guarantee that my demonstration will not be boring, but can you confirm that you see my screen now?
Yes, we can see it. Okay,
thank you. So I prepared a little bit of a hopefully illustrative demo. You can check out the exact demo that is also shown in a YouTube video on our YouTube channel in Elmer FEM. It's this parallel demo of Elmer. You can check the input files and even more than what I showed today. So I just confine myself here to a small subset, including actually already an input file for the experimental branch of the AMGX library, the thing I just answered in the Q&A. So what is it about? It's about a flow coming here from left to right, and basically having the letters of Elmer as an obstacle in the channel. The flow is chosen such that it is, with respect to the Reynolds number, still able to be solved without any turbulence model. So the simulation or the solution then looks like that. So it's a transient case with the flow starting from 0 velocity and then building up for the next 20 seconds. Right. So to shortly demo you, if you check out from GitHub the repository, it will look like that here. So you will start with a geo file, which we can, using GMSH on the pure text interface, shell interface, to mesh it. So we calling GMSH, which is installed on my machine, giving Elmer underscore flow.geo as the argument, and then GMSH should start meshing it. You see that it's 124,000 elements about, and about 57,000 vertices. Right, so after having done that, maybe we make a listing like that. We should have a mesh file in Gmesh format. And now the point of time comes, as Peter said, where we utilize the Elmer grid command. So we use Elmer grid. Maybe let me make that larger. Elmer grid, and then we have these magic numbers in Elmer grid. You can look them up actually by giving Elmer grid without any argument. So if you do that and then scroll up, you see that you have input and output numbers. And if you look for Gmesh format, you will see that number 14 is the input format, and the Elmer solver format would be number 2. So what we are doing then is calling Elmer grid with 14 and 2. Naturally, we have to give an argument which file we want to work over. Sorry, this is not the geo file, but the mesh file. And then GMSH has the feature that it does discontinuous numbering of bodies and boundaries. So what we have to call from the Elmer grid side is to do an auto clean. So if I punch that in like that, I would get a serial match, which I do in the beginning here. So if I now make a listing, I will see a subfolder with the serial mesh. And if we look into this one, we see these 4 files. So the mesh header, mesh nodes, mesh elements, and mesh boundary, which is kind of self-explaining. So all finite element programs kind of produce similar meshes with this kind of information. So now we would be ready to go for a serial run, which I want to shortly show you the solver input file for. We are using a new version of the Navier-Stokes solver, which has OpenMP directives, both for multi-threading as well as, this is maybe more important here, for SIMD, so using the vector units of the CPUs implemented. And we're using a Krylov subspace method with a, I think, ELO1 preconditioner. Let me change to that block here. Yes, correctly, which is a Krylov subspace method, GCR, for solving the system. So what we can do now is going for the solution of that, having created our files, but I think I'm in the wrong department here. Sorry for that. Short hiccup. It's always this on. What? Sorry for that. Short hiccup. So yeah, here we are. I was in this directory. So we can immediately go for the Elmer solver serial run, and then for the corresponding file, which is Elmer flow GCR CIF. Sorry for the short confusion here. And then opening another console running HTOP, we see we have a single core of my 6-core CPU now engaged. And after some times, we will get here reliable estimates on how long it takes. So let's take a note after the 3rd step, then I make a break on that. So it's about 3.7 minutes left after the 3rd iteration. So since you can see here, I have a PC with 6 cores. I'm, of course, inclined to use all of them because I paid for them. And for that purpose, we have to go for either multi-threading or MPI type of runs. So you could also have, now with the serial mesh, a simple multi-threaded run by declaring, provided, of course, you have a version compiled with multi-threading, aka OpenMP activated. You can declare your OMP num thread to be, in this case, for instance, 6, according to my computer, and then run the case as if you would run it in serial. So Elmer solver with the same CIF file, nothing has to change there. And then you punch enter, and you see now, hopefully, yes, at least in parts of the simulation, all the 6 cores will be engaging. Multithreading is very difficult to really get it to scale, so you really have to address all the blocks. As soon as you have a serial block therein, it automatically will be the bottleneck. And that means it is not as fast at the moment as the MPI, but you can see 2.8 instead of 3.7, I think it was, left at the 3rd iteration step. So there is already something gained here. Okay, but now we want to go for the full thing. So we want to utilize the MPI paradigm inside of Elmer. And for that, we have to partition the mesh. So you basically running, in my case now, 6 Elmer solutions. And for that, you have to provide 6 mesh partitions where these solutions can be run on. And then we have to return back to the Elmer grid command. And we want to change an already existing, namely Elmer flow grid, into a parallel grid. So we are doing Elmer grid 2.2, giving, oh sorry, I'm missing the E here, giving the subdirectory where the serial mesh exists as an argument. And then we are choosing a certain way of partitioning, better already presented. So I'm using part dual and metis k-way, and then give the number of partitions I want to have. Hope I didn't mistype it. Then I punch enter. No, it worked. So you see that the mesh then basically is split into 6 partitions here, showing that this is very important for load balancing, the amount of elements as well as nodes per partition, and also the amount of shared nodes. That's where the communication, the MPI communication has to take place, are quite okayish distributed. Of course, if you have a confined mesh without periodic conditions, you always will have parts that have less shared nodes than the others. That's just by geometrical considerations inevitable. Okay, so what has changed? Let's take a look at the Elmer flow subdirectory. We have, as you might spot here now, a subdirectory called Partitioning 6. And if I make a listing of that particular subdirectory, you will see now that we have a 6-fold copying or 6-fold occurrence of all these previously only in the serial mesh existing files. So we have headers, nodes, boundary, and elements. On top of that, we have for each partition a shared node list added. So this is this .shared file. But else, basically, it's just a submesh for each partition. Okay, so now we are ready to fire up the Elmer simulation. So as I said, the paradigm here for running parallel is MPI. That's why we need an MPI run. We have to tell MPI how many cores we want to use. I partitioned into 6 partitions, so I will have to utilize 6 cores. Else I would get an error if there would be no existing mesh with that number of partitions. And then, yeah, the syntax is exactly the same. The rest of the syntax, so Elmer solver, and then the argument of the CIF file you want to execute. And we stick with the same CIF file. Important to mention here, we haven't changed anything in the CIF file, so the GCR method will be just now deployed in for each partition, and then using MPI for communicating and converging on the global level. So I punch enter, And if you look at the h-top on the right-hand side, you see that now basically all 6 cores are on 100% all the time. And let's have a look at the timing. Yeah, we are down to 1.5 minutes, which is way quicker than the versions before. And I think I leave that running now, and better, I think the plan was to come back and then have some short demo on how to post-process that once it's done. So I stop sharing. Better?
Yes.
Okay, yeah.
I'm here. I just need to start sharing again. Okay. I hope you can see the screen. So you had the demonstration. Now I will sort of continue. So a good question is, how does the partitioning affect the matrix structure? So, you know, we are working with sparse matrices. So if we would have a serial mesh, we would be looking at something like this. So you can see that the sort of, because this is regular, the numbering of the degrees of freedom sort of has certain pattern, and you can see this in the bandwidth of the matrix. However, if you then make a parallel mesh, then each partition will own its own color, so to say. So you can see this reflects the colors on the that you have for the Winkel geometry there. So, and these then off-diagonal entries, they are the shared degrees of freedom, and the owner is then, or the color is representing the owner. So these are the ones that you need to communicate. And sort of that is the challenge in parallel computing, and the solution of linear systems in parallel, that you need to be able to communicate these sort of, or at least the effect of those. So you have many different implementations of how to deal with that, but that's a typical one. And this communication cannot be eliminated. It sort of reflects the local interactions of the underlying partial differential equation. So the partial differential equation has like local interactions, and that is reflected then that also the discrete description of the same system must have similar local sort of connections. And if you have an unstructured mesh, your mesh will look a little bit more different, but again, you will have sort of rather complicated matrix structure. Of course, how the matrix looks like depends a lot how you do the numbering, but here we have numbers so that using the numbers starting from sort of first partition, etc., so that roughly the sort of numbering of nodes follows the partitioning numbering. And when you have sort of like vector value problems or higher order problems, then you will typically have more of the shared degrees of freedom. And you see also here the challenge of partitioning. So the challenge is to find a partitioning that minimizes the sort of off-diagonal entries in these matrices. Thomas already showed you the sort of matrix structure of Elmer in serial and parallel. So in serial, the mesh lies in under a directory, and it's really a simple sort of data structure consisting of 4 different parts: the header, the nodes, the elements, and the boundaries. And if you have a parallel simulation, then you have exactly the same, except they are given for each partition, and they are saved on a partition-specific subdirectory or partitioning-specific. So if you would be doing like 32, 64, 128 partition jobs, they would all get like different partition. I must say that I didn't prepare any slides, but there is work going on. It was actually initiated in the Elmer ICE community by Joe Todd and colleagues about partitioning inside Elmer, and we did some collaboration, so it's possible to do some sort of master-slave type of partitioning. It's under development, and this is still the main strategy. And this is nice in that it doesn't introduce sort of asymmetry in the processes, so you won't end up having one process being significantly larger than the others. So if you have this master-slave type of problem, then running thousands of cores would probably exhaust the resources on the first partition. But then if you use this internal partitioning, then this sort of parallel mesh structure does not, of course, exist. And then running the case in serial, we run like this, and in parallel, we have an environment-specific way to run the parallel jobs. So, and then the results, we typically use VTU files because they are really nice. They are binary. They are automatically supported in parallel. So in serial, we have one VTU file, and in parallel, we have several VTU files, and then a PVTU file, which is a wrapper of all the different VTU files. And parallel post-processing is almost the same in serial and parallel. Of course, in parallel, you may be more sort of exhausted by the resources, but other than that, it's typically exactly almost the same. You just open the PVTU file instead of the VTU file. Here we did actually this week some sort of refresh some of our old benchmark problems. So this is a scalability problem involving a cheese. So why this cheese? So I made a sort of this kind of case where we sort of randomly create holes in a geometry because it's easy way to sort of increase the number of holes and thereby increase also the complexity of the problem as the size of the problem grows. So you can sort of give the number of holes and you can get increased sort of complexity to the problem. Anyways, we solved another problem here, so which is basically a linear elasticity problem, and tried out our own implementation of a conjugate gradient plus incomplete L loop, and this worked pretty nicely. So, so if the task is large enough, like here we have 20 million unknowns, we certainly can get quite good sort of strong scaling even for the larger jobs. So it's really difficult to sort of always sort of analyze why are these graphs as they are, because there is a complicated memory hierarchy and I/O patterns. So it's not easy to predict what the final outcome will be, but you can see that at stages we follow this ideal sort of strong scaling. So this means that if you double the number of cores, then the time should go or be diminished to half. So this is the ideal, and at times we follow that, but like here, when the number of partitions grows too large, then the relative fraction of communication increases and you cannot maintain that. Here is another example. So here we use PCG stub L and no preconditioning. The reason why we don't use preconditioning here is because this is a AV solver example where we use H-curve conforming elements, and we don't use here a gauge condition, which means that the solution is not unique. Actually, it's made unique by by the Krylov process itself, but there is no inverse for it. So we cannot use incomplete LU, for instance, which we typically use. So none here means that we still use scaling, but you can see that anyway, we get nice sort of scaling here. So even for the largest problem size, which has some 50 million unknowns, we get scaling, quite nice strong scaling up to 4,000 cores. So of course, in both these examples, I'm not saying what the sort of weak scaling is, but at least strong scaling, which basically means that the implementation of the method is done properly. It's good. I think, Thomas, we may now be going to see whether you actually did compute something. So.
Yes, moment of truth.
Yes.
Share my screen. If I don't hear anything, I assume it's working. So so let us see. Let's have a look. We can do a listing, actually in temporal order of Elmer flow directory, excuse me. And we see, yes, we seem to have a result up to the 20 time steps we have been producing. So next step then would be to launch PowerView. Assuming, of course, that it's installed on your machine. It is on mine. And then one can go to the subdirectory, of course, and then one can load the parallel set of files. So these PVTU, they kind of are header files that enable you to load the different partition files. Okay, so don't go for these VTU files. There are actually zillions of them now, actually 6 times 20. You want to load the whole set of parallel VTU files. Press OK. And then people often think, okay, what's happening? I can't see anything. PowerView demands you to press the green apply button, and then you will be provided with a picture of, in this case, our Elmer mesh, already with a variable displayed. I guess it's simply the first one that's available. The pressure, you could have the velocity, which in this case wouldn't bring you pretty far, because as you can see, we have no slip conditions all over the place on the boundaries. So there is zero velocity by definition there. So what you want to do is make a slice, for instance, through the element. You can do that with this slice filter. We want to have it in the set direction, I think. Yes. And then press apply. And by that, you now can nicely show the velocity and also animate it. You see that the thing is ramping up and getting faster here on the corners, and then developing some vortices even after some while. One nice feature I can show you of this is also PowerView has a filter that can display the connectivity, aka the partitions of the mesh. So that would be a filter called, if we go for the alphabetical order here, connectivity. It's always hard to tell the forest from the trees here. Here, particularly if you are doing an online demo. And you nicely can see, if we switch in actually additionally the edges, you can see that the partition has been taking place according to the number of elements being involved, and also trying to equally distribute the interfaces between the different partitions. And you can really build up quite nice sceneries with PowerView. Let me demonstrate that. Like, for instance, producing this one animation that is on the YouTube channel, as well as on the GitHub. So taking different slices, also stream traces. You can have a source here that then computes you the stream traces, and then you can color it with the color of the velocity, and then you can make these nice animations like the one I showed you before. Right. That's, I would say, I guess, all from my side. So I guess, Peter, you want to continue?
Yes. So you saw some simple benchmarks computed at CSC. So unfortunately, the world is not always so simple. So these basic linear solver libraries, they work great for many standard problems. So you can easily get scalability up to thousands of cores. Unfortunately, there are some complexities in the world. So you can have like unsymmetric problems. You can have constraints in your problems. You can have compromised mesh quality. You could have like a circuit equation added to the problem, etc. So it's not always so simple, the equation that you want to solve. It may be something very different from the prototype problem of ideal Poisson equation in a unit cube. On the other hand, the target number of cores is often not that huge, so it may be hundreds of cores or even just tens of cores. But direct solvers may still be too slow or memory intensive, so they are not an option. So often we have to little bit sort of look for good strategies for such problems, which are sort of have some complications. And one such strategy that we have used in many problems is block preconditioning. So this is applicable to partial differential equations associated to vector fields. So you can have like Navier-Stokes equation or elasticity equation. And the idea of block preconditioning is that you use a preconditioner, which is a procedure where the components are sort of solved one by one, and this solution is used then as a search direction. So you have this blockwise done solution done in some Gauss-Seidel or Jacobi manner, and this process then creates search directions that are used by the outer level Krylov method. And the nice thing is that mathematicians can show that the number of these outer iterations is bounded. So it has an upper limit, which is nice because it's not self-evident that you would have an upper bound for the number of iterations. And then the individual blocks, they become simpler and may be solved with optimally scaling methods. So this would be multi-level methods like multigrid methods. So this is sort of more mathematical description. So you have a block system. So this, for instance, this would be a Navier equation, linear elasticity equation, this would be K11 would be the sort of block 1 that is associated mainly to the first displacement, the x displacement, and K22 would be associated mainly to y displacement. Of course, you have also the coupling terms, but for the sake of the sort of preconditioning, you may forget about the block coupling terms or use sort of lower diagonal preconditioner. So this would be block Gauss-Seidel, this would be block Jacobi, and this sort of solution of this system blockwise then produces you the search directions that you use in the GCR method to minimize the residual of this problem. So that can work quite efficiently. So as a motivation for using that kind of problems, this is our old friend, the cheese. So here I compared many years ago already. So on my laptop, I think the CPU time that is needed for a solution of the linear elasticity problem using two different methods. The first one was BCG stub 4, so with an incomplete LU 1, which means that the sort of incomplete LU includes all the components that comes from A times A matrix multiplication, and then GCR method using a block preconditioner, which uses algebraic multigrid for each component. Well, sounds complicated, and it's certainly is a little bit complicated, but when you start from the smallest problem, you can see that they are pretty much giving the same CPU time. So with 8,000 degrees of freedom, I get like roughly 1 second for each. You think that, okay, actually it doesn't matter which one I use, so you start using this BCG stub with incomplete LU, and you do tricks. You increase the mesh size 3 times by dividing each edge. So basically every time you get 8 times more degrees of freedom. So the largest case then includes 2.3 million degrees of freedom. And actually you can see that after my PC running for the whole night, I could not get any convergence, because I think I didn't want to sort of wait anymore. It took already like 21,000 seconds, which is maybe 7 hours or 6 hours. But this multigrid preconditioned version using block preconditioning took only 12 minutes for 2.3 million on my then laptop. And the number of iterations with the mathematicians promised that would be bounded. Well, it grows a little bit, but I could figure out that it's bounded, so it doesn't grow, at least exponentially. And the scalability for this problem is 1.03, so almost as the theoreticians promised. So the theoretical maximum should be n log n. And here, Mika Malinen has shown this to be also valid for Navier-Stokes equation. The recipe is a little bit more complicated there. I don't want to go into details, but so you have to sort of do some special tricks for the pressure component. But anyways, if you do the tricks properly, then you can come up with the scheme that almost scales sort of optimally, even weakly. So here we have grown the problem. So I think the problem is like, well, it's 4 times larger in each direction. So that means it's 64 times larger, but the time just grows with a factor 2.5 or so. And this has a scaling law of 1.14. So it's pretty decent for such a complicated problem. And this actually is now implemented as a method to the incompressible Navier-Stokes spec, which is the new generation solver that the Elmer ICE community uses, which has also some other bells and whistles, such as the threading that Thomas was demonstrating in the demonstration. So not all versions or models of Elmer are threaded, but this one is. And yeah, you already saw some ways to increase the mesh density. So often you don't want to be bound with your meshing process. So you want to maybe go a little bit to a larger problem, but if you have a serial meshing process, then that might limit you. So what we often do is we add a parallel process, mesh multiplication or mesh extrusion. So we finalize the mesh on a parallel level. So we have some ways to do that. So you can basically partition the mesh and then do the tricks on parallel level. So we have a mesh multiplication where you take a mesh, split each edge, and get, like in 2D, you get 4 times the number of nodes, or sorry, elements, and 8 times the number of elements in 3D. And actually, the number of nodes grows roughly the same, but not, of course, exactly the same. And there is also a simple inheritance of mesh grading. So you can a little bit conserve the mesh grading. You can also increase the element order. You can extrude the 2D layer for 3D. So you start from a 2D geometry and extrude it to the third dimension. And unfortunately, of course, these are not always possible for complex geometries because the sort of geometric accuracy of the problem is not increased. But other than that, these are often sort of very nice methods. So here is an example. So here I say, in simulation section, I just choose the mesh levels. So mesh levels 1 means that it's the original sort of density. Mesh levels 2 would make one split of each edge, and the mesh level 3 would do it 2 times recursively. So for instance, if I here started with 33,000 tetrahedrons, then mesh levels 2 gives me 270,000 tetrahedrons, and mesh level 3 gives me 2 million tetrahedrons. So this is an easy way to try to sort of increase your problem size, which is the method that we use in our sort of supercomputer benchmarks and often also real simulations. And here is the other sort of method that you can use. So it's the internal mesh extrusion. So starting from 2D footprint, we can extrude it to third dimension. And of course, we have methods to sort of make the sort of height sort of reflect the sort of true sort of height. But here, my emphasis was mimicking the Alvarado design here. But it's easy. You just in simulation section order how many mesh levels you want to have, and then you have it created for yourself. I think I had a slide on how this is applied to Elmer eyes. So basically, this is the main strategy that has been used for in computational glaciology. When you have huge continental ice sheets, they still need to be resolved using 3D methods, but you can get the sort of footprint and then extrude the third dimension and avoid all the bottlenecks in the sort of pre-processing, or at least most of the bottlenecks. A few words about some ongoing developments. Thomas, do you want to go through these slides, or because you have been more active on this field?
Yes, I could. If you just leave your slides open, I think this is most convenient, so that I don't have to share forth and back. Yeah. So, well, I think I already mentioned that at least at some level that we have SIMD instructions using OpenMP there. So OpenMP is good for two things. One is vectorization. This is exactly the SIMD part here. And the other one is multi-threading. So for both, you need OpenMP to be activated. There was also a question in the Q&A. So OpenMP is activated. You don't have to really link something actively to it. It should be included in your compiler suite, like for instance, the GNU suite, but also commercial products like Intel have OpenMP enabled. And to enable it really in the compilation or in the configuration for the compilation for Elmer, you have to switch a flag with OpenMP in the CMake command to true. Then it will start looking for OpenMP and include it. The same is for MPI. You need to tell the CMake to have with MPI, and then most likely will find your system MPI and then include it. And for vectorization, this is quite important for modern CPUs. So you easily use a quarter of the actually 3/4 of the possible performance of your CPU if you cannot utilize the vector units on it. So modern CPUs are really in need of a good strategy for vectorization. Well, I guess that's also naturally vectorization needs to. It's basically a concept where so SIMD is single instruction, multiple data. So you have to provide a large array of data that can be processed with the same instruction. So having more Gauss points in your element helps to do that. So we have, for instance, simulations now in glaciology where we have 44 Gauss points for one element. And then you can just treat the whole element in the vector unit, and this will be very effective. Okay, can we have a look at the next slide, please, Peter? Yeah, this was multi-threading. Yeah, multi-threading is a thing that is a little bit difficult. So the whole thing started to be important, and also the vector, the SIMD implementation in a connection with a project we had together with Intel at the times where they still were developing these many integrated core systems like the Knights Landing system. And there we had quite nice speed ups. But the problem is you have to address every solver and every part of it to have everything always multi-threaded. And this is really a lot of work. It also often needs rearrangement of data structures, etc. So this is a lot of programming work. And like Beta said, this new Navier-Stokes solver is a consequence of that. Basically, what you then often do is trash the legacy solvers and just start from scratch, because this is often easier. So then to renovate a house for completely new purpose, you usually tear it down and start from scratch, building it. Okay, let's have a look at the last slide then. I guess this is about the EMGX, yeah. So I dropped the information that we have an experimental, also in the Q&A, experimental branch of Elmer that enables the offloading of the linear solution step, so not the assembly, to GPUs. And this works quite okay. In contrary to what actually I claim in the YouTube video where I demoed that, it actually with a certain newer version of EMGX already works in combination with MPI. So then you can do the assembly on MPI and then offload to the GPU. This de facto really makes only sense if you're on a HPC system with multiple GPUs, for instance. And on the right-hand side of this slide, you can see some experiment done with Navier equation. So linear elasticity with a combination of different MPI tasks and GPUs from our Buchti system. And we found, at least for that problem, that size, quite nice speed up, as well as found out that you really have to cleverly make the combination between MPI tasks and GPU to hit the soft spot, which in this problem was 4 GPUs plus 20 MPI ranks. So this is work in progress. If you utilize that, then it's on your own risk. We are still developing that. Hopefully, we get resources for that. And further plans, of course, would be nice to include the assembly also be done on the GPUs, which, to my knowledge at the moment, and I'm not a specialist in GPU programming, would demand the deployment of a special version of OpenMP that allows for offloading to GPUs. But that's in far future, so we have to find also some projects to fund that, I would say, because this is a lot of work to do. Yeah, I guess that's it from my side.
Okay, I still have a few words about so what can you do if you want to sort of avoid some bottlenecks in your simulations? So as said, know your algorithms. So you should know how they scale, and even if you are accustomed to certain algorithm when you have a small job, then growing the job also may mean that you have to change your algorithm. So for instance, that would be often that you are very happy using direct solvers for small tasks, but when you go parallel and go into larger jobs, then that's not a feasible strategy anymore. So you have to use something else. Generally, the strategy, if you have a hard problem, is like often in life, that also in numerics, if you have a really tough problem, so try to divide it into simpler subproblems. So for instance, in vector valued problems, this may mean that we solve one component at a time, and then we end up having sort of block preconditioners. We can also sort of solve one domain at a time. So we have different, that generates then like domain decomposition methods, and we for instance in Elmer we have a FETI method, which I didn't mention, but it scales like weak scaling is superb. The challenge is to find large enough cases, linear cases where it is sort of applicable to. So if you have huge cases, that FETI method where you sort of solve one domain at a time and then have a different equation to sort of combine those solutions is maybe of use for you. And then like for flow simulations, you often split your Navier-Stokes equations. So you have different kind of splitting schemes like MISO or whatever, pressure correction, velocity correction schemes. We don't so much have those. There are some like alpha implementations, but this is sort of the general rule that if you have a difficult problem, then simplify it by splitting it to simpler subproblems. And one problem may be sometimes the sort of pre and post processing. So if your job grows very large, then you may have bottlenecks on the pre-processing, and here the mesh multiplication, mesh extrusion, and even parallel mesh generation, which unfortunately there is no sort of, there has been experimental work on that, but there is no sort of method that comes with Elmer on that. There has been some papers on that, but mesh multiplication and mesh extrusion in parallel may be still something that you can use. Also for post-processing, it's often a good idea to analyze the results on the fly. So we have a lot of features where you can sort of analyze the results. No need to sort of save everything and then open ParaView and try to then sort of analyze what's the data in one particular point. You can instead just save that one particular point to start with. Or if you want to study what the data is on a given line, why not just save the line? So these kind of sort of reduction techniques, also like reducing, computing the integrals, etc., inside the code makes often sense. And then if sort of there are new developments in the architecture, then of course following those, and that's mainly our business, so to follow the developments in the architecture and try to take use of them, because the sort of yesterday's techniques won't probably work so well on tomorrow's computers. Yeah, so I think that was about it. So do we have some questions? So I think I didn't answer some questions, so they are there sort of to be revisited. So maybe Thomas, can you read? There are some questions.
Well, I answered the most already typing in, but there are two questions pending about the motor, I think.
Yeah, I will answer this. There is a question from Felix: how to choose with which solver type, direct or iterative, one should start to simulate a problem. Is the decision different for serial and parallel computing? Yeah, I would say that if you have a very small problem, then often starting with direct solver is nice because you sort of can eliminate one cause of problem. But then, of course, you can compare that to the iterative methods, and if they are faster, then why not use them? But I would say that if your problem is large enough because of the scaling laws, you remember the scaling laws for direct solvers, it was roughly like in simple 3D problems, the scaling law was roughly like quadratic. So if your problem size grows with a factor of 10, then your CPU time will grow with a factor of 100. So of course, if you go from small problem to quite a large problem, then you will really feel that. In 2D, this is not so dramatic because the bandwidth in 2D tends to be smaller. So I would say that in 2D, the scaling law is easily 1.5, and then it's more sort of easier to compete with the iterative solver. So yeah, I would say that why not start with direct solvers, but only sort of like in the first small cases, and then you can compare them to iterative solvers. And I think we mainly only use iterative solvers, except when sort of the shit hits the fan, so there is no sort of solution to be found, then you maybe have to take months and just bear the time that it takes. It's better to have a slow solution than no solution at all. Was there other questions?
Yes, there are still 2 questions left.
Maybe you can ask them.
Yes, okay, I can. So one, I think, refers to an earlier question about 2 second-order triangular elements. I don't know exactly how this links. And one is about elaboration on conforming and mortar boundary conditions in Elmer. Yeah, these are the 2 open questions left.
Yeah, so in the last presentation, there was quite a bit about conforming and mortar boundary conditions. So yeah, in short, the conforming boundary conditions can be used if you can map 2 boundaries together so that they join or share the nodes or edges, and it's applicable to like both to the nodal and to the sort of edge element problems. Then the mortar machinery, it is sort of results to much more difficult linear systems, but it has no such constraint that it can be sort of, it's limited to sort of conforming meshes. So typically, for instance, I think the person asking the question was from the electrical machine community. So typically there you would, the angle, if you have model a symmetric part of the machine, you would typically could use for the sort of symmetry of the angle, you could use like the conforming boundary conditions, but then on the rotating boundary, you can never use the conforming boundary conditions, but there you have to use the mortar boundary conditions. And you have to do some tricks in Elmer grid to sort of confine those sort of 2 boundaries that you want to sort of have to be continuous. They must reside on the same partition, or at least you must have the halo such that you can form the mortar projector. So this is sort of an additional nuisance for the user that he has to do that. but I maybe don't want to go into detail. But so the projectors often adds complexity to the parallel systems. Do we have any other interesting questions?
No, I don't know what this question about second order triangle elements links to. That is still in the Q&A. So except for that, no, we don't have any questions open. And then anyhow, I think we are heading towards the end of the...
Yes, I think you can look at the triangular element from the solver manual appendices. So.
And anyways, if you have unanswered questions, you can always perhaps look them up if they are already answered in the forum. Else, then post them in the forum.
Yes, so I think we are finished, and maybe even finished before the 90-minute deadline. So Mikael will be happy. So yes.
Yes, and yes, this was a 90 minutes, just 3 minutes under. So we'll make it. Thanks to everyone for participating, and we'll continue next week on the 1st of April, and the topic is Elmer Open Home Library, and our speaker is Juris Svensels. And the recording of this will be available within 1 week, approximately, on the Elmer FEM YouTube channel. And we have our previous recordings there uploaded already, so you can take a look there. Otherwise, on my part, big thanks to our speakers again, and hope to see as many of you as possible next week in 1 week's time.
Yes, thanks, and see you in 1 week. And I promise you, it will be interesting. So bye bye.
Thank you. Bye.